If you've done any grading, you probably know this. I mean, the first thing you look for is whether the person got the correct answer or not. And then you start looking through the steps of whether they got there the right way. I mean, and ultimately, you only really want to give full credit to the person who gives a correct justification and addition, but you get really pissed off if the person is also giving you the wrong answer. So yeah, right answers are very important. Okay, office hours. So this is the exam. I've written it in large writing, so it should be very clear and you should not miss it. Also, remember that your name has a sort of multiplier effect, right? I mean, if you do not put your name on, you get 0 on the exam. So you want to get that first part of the exam spot on. That's a very important part of the exam. Now, Peter Anderegg has extremely generously offered to run many, many office hours. And so, I mean, Liz may also offer some in-person office hours. I'm also, along with Liz, available by email. But as I said, Peter Anderegg is offering a lot of office hours. So you might want to mark these down. I think he sent out an email, but just make sure you have a note of this and you don't delete the email or anything. So coming up tomorrow, so Saturday, January 17th, 4 to 5:30 p.m. And Wednesday and Thursday, January 21st, 22nd, 4 to 6 p.m. And these are both in the 4th floor math department lounge. So lots and lots of office hours. You should, if you're feeling at all weak on anything and you want some feedback about what exercises to try, Peter Anderegg might be a very good source because he can work through any problems with you, for instance. And that's actually a really good way, of course, preparing for the final, just running through lots and lots of problems, trying lots of things that you weren't comfortable with, because then you'll get comfortable with them. So anyway, last time we went through the subjects treated in the first 2/3 or so of the study guide, which is online. So I mean, if you go online, to the Math 122 webpage, there's a heading, Final Exam and Review, or something like this, and that has useful links and resources and so on. So it has a link, for instance, to the study guide. I sent an email about that previously. Also, the links to the videos and notes from these review sessions are going up. The one from Wednesday, the notes and video from Wednesday are already up on the webpage, so you can go get those in case you had to miss that for whatever reason. And so now I'm just going to continue slogging through the study guide. By the way, the study guide is in many ways more useful than what we did in the review session last time, because the review session last time wasn't necessarily entirely targeted to the exam, whereas the study guide, which I'm probably going to update shortly, is very much sort of targeted to the exam. So there you go. Okay, well, I'm going to get on with rings. Okay, great. So I'm going to say a lot of redundant things. I mean, a lot of this is really straightforward, but I mean, this is a good time for you to actually just, look at each of the words that I write and make sure that, you feel, totally comfortable with the words. And if you don't feel comfortable with the words, you should definitely make a note of it and, go through and review those words carefully. So we're talking about rings. So I mean, you better know the definition of a ring. So you better remember that you have some sort of addition operation. This is an abelian group. That there's some sort of multiplication operation, and this thing is associative with one. It has this multiplicative identity thing. And in general, we assumed that this operation was commutative, although we looked initially at the non-commutative case as well. and there's some sort of distributed property that relates the addition and the multiplication. And we saw lots of convenient first examples that came almost immediately out of our study of group theory. So we have a sort of trivial ring, which is, I mean, in some textbooks that's not even considered a ring. I mean, sometimes it's completely excluded from the discussion. Other convenient examples, the integers. We'd already introduced the integers modulo n, and so we saw also previously in the section on modular arithmetic that a z mod nz forms a ring. You should be very comfortable with arithmetic in z mod nz. You should be able to quickly look at things, mod small numbers, and be able to find interesting examples of features of that ring. And bear in mind things like when does that thing have nice sort of field structure, and why does it not have nice field structure in the composite case. Of course, any of the fields that were germane to the section on vector spaces were rings. And given any ring, you could construct a polynomial ring. In fact, you could do funny things like construct polynomial rings and infinitely many variables and stuff like that, although that isn't going to be a very important sort of example. And sort of as the analog of the normal subgroups from our discussion in group theory, we had ideals. These are the things that arise as kernels. But saying that the definition of an ideal is the kernel of a ring homomorphism is probably not the ideal definition, pun intended. And you should really define it as being an abelian, something that's a subgroup under the addition law and which is closed under the multiplication operation. So subgroup under plus closed under multiplication by all of R, not just by I, the ideal itself. And I mean, we saw lots of good examples of ideals. We saw principal ideals. Or more generally, we saw ideals generated by a certain number of elements. So these are all linear combinations. All linear combinations of those elements. And we saw a very, very important sort of operation. This operation turned up later in our sort of number theoretic study. This is a very, very important definition. And that is that if I have two ideals, I can construct a new ideal, the product ideal. And these were all sums, AI, BI, where the AIs are in I and the BIs are in J. You need to be able to not just take single products, sort of monomial products of things in I and J, but more extensive products of elements of I and J, because otherwise the thing would not necessarily be a subgroup under the addition operation of the ring. We saw homomorphisms, ring homomorphisms. So, and of course, these are things which preserve the addition operation, the multiplication operation, and because of the way these things work, you need to additionally specify explicitly. I mean, you need to verify explicitly that ring homomorphism preserves the multiplicative identity. Otherwise, you don't necessarily have something that's a ring homomorphism. Of course, the kernel of ring homomorphism is an ideal, and the image, so it was an ideal of the domain ring, and the image is a subring of the target ring. And so those are sort of obvious things, but there were some very good examples. I mean, there was a sort of canonical example which we exploited of a ring homomorphism. If I have any ring, then there's a natural homomorphism from the ring of integers to that ring. So this is for any ring R, and that's just defined by sending the multiplicative identity of Z, namely 1, to the multiplicative identity of R, namely 1, and then just using the obvious sort of addition properties to fill out that homomorphism. And it's, of course, easily verified that that is indeed a homomorphism. But the point of that was that we could exploit that to understand some very, very important structural aspects of rings. Among them, we use that, for instance, to understand finite fields. We exploited this precisely to understand what are the finite fields, like identify what are the possible finite fields. And then later on, we saw the background for why all of those were realizable. But we gave what was the largest possible set of finite fields using just an understanding of this homomorphism. So applied structure of finite fields. And another feature of rings, so the addition law obviously gives rise to a group, but there's another group that you canonically associate to a ring, and that is the multiplicative group of that ring, or in the main terminology we used, the group of units. So denoted R cross or R star. These are the elements which are invertible. So there exists beta such that alpha beta is the multiplicative identity. And in nice examples like fields, that was everything except 0, for instance. We saw, building on notions of ideals and homomorphisms, quotients. So you have a quotient R mod I, and of course, when you have such a thing, there's this canonical homomorphism from the ring to that quotient. And just as in group theory, the notion of quotients led to isomorphism theorems. So we had the first isomorphism theorem, which, of course, said, just like in the usual case, that if I have some sort of homomorphism phi, then R mod cur phi admits an induced homomorphism from this phi to the target ring, and this thing is injective. And along those lines, we had that you could understand the ideals of a quotient in terms of the ideals of the initial ring under sort of basic correspondence. Ideals of R mod J correspond to ideals of R containing J. So, and I mean, there was a third isomorphism theorem that said that, in fact, not only do they correspond, their correspondence is so natural that when you take quotients, the quotients are isomorphic to the quotients under this correspondence. Yes?
There's a more general form of the first isomorphism theorem, too. Is that like ideals containing other ideals?
Yeah, so I mean, that's the second isomorphism theorem. The second isomorphism theorem tells you what's the correspondence between ideals in a quotient and ideals in the initial ring. Now, if you start out with a homomorphism, that induces, I mean, that thing corresponds to some sort of ideal of the ring, and you have, you can sort of rewrite this with J being the kernel, and then you will have, as you say, a statement like that. If you have a ring homomorphism phi from R to R prime, the ideals of the image of this homomorphism, since that's isomorphic to R mod the kernel, are going to correspond to the ideals of R containing the kernel, but that's just a accumulation of those two statements. It's not actually a generalization.
I think that in the book, the first isomorphism theorem was listed as a special case.
Okay.
This kind of more
Uh-huh.
And I mean, I'm just wondering if we're going to be responsible for that too.
Well, I think that all of the things that are called isomorphism theorems follow pretty much immediately from those two statements. Well, I mean, and the sort of third statement I made, which is that the quotients are isomorphic under the second correspondence there. But I can't think of anything actually really more general than for the first isomorphism theorem for the first than the first statement. I mean, it's actually more general than the way it's usually stated in books. I mean, there you have it start with a surjective homomorphism, so but I mean, these are all trivially equivalent, so it's probably not a big deal. I mean, you should be able to deduce from these statements whatever statement you need. I mean, in fact, the isomorphism theorems are essentially tautologous anyway. I mean, you should now be at the point where you know exactly the proof of the first isomorphism theorem in either the group or ring cases. It should be just completely immediate what's going on. I mean, math researchers at some point don't even call these things isomorphism theorems anymore. I mean, it's just you just sort of write it down, and it's just sort of automatic. You know why the thing works. Because, I mean, it's just the sort of general idea that if things are contained in the kernel, then since they're sent to something trivial in the target of the, whatever morphism you're dealing with, those differences don't matter. Anyway, one of the major uses of this quotient construction was the creation of relations. So I mean, lots of very, very simple examples of creation of relations. So suppose I start out with polynomials over the integers, and I now want to somehow construct a new ring out of this thing such that x squared is minus 1, then I do the obvious thing. I want x squared plus 1 to be 0. So I quotient by x squared plus 1, and I indeed get now a ring which has this element, this formal element, which has as its square minus 1. And this is just the ring of Gaussian integers. So creation of relations is a very, very simple idea. And there's a bit of a warning on that. Be careful with what you think creation of relations actually does. So for instance, you might think that if you would make x satisfy the property that its square is 1, then you would have just the integers back. In fact, if you mod out by x squared minus 1, you do not get the ring of integers. You get the integers cross the integers. And so understanding why this happens is a useful point. I mean, you presumably remember how this works. I mean, if I have an element alpha in the quotient here, and I'll just think of it as actually being a polynomial over the integers, so alpha of x, then I can, for instance, get this thing by evaluating at plus 1 and minus 1. So alpha of 1, alpha of minus 1 induces an isomorphism. Okay. So then, sort of moving on from this creation of relations, I mean, you can assume that you're just starting out with some sort of polynomial ring over a ring, and use this construction to very precisely adjoin elements, much as we were doing here. Junction of elements. So, I mean, at some point, we wanted to do things just like there. So, we started with the integers, and we wanted to do something, say, like adjoin a square root of 2. So, we use the sort of notation z adjoin square root 2, and that was just z adjoin polynomial ring over x modulo x squared minus 2. But there was another sort of thing that we did, and that was we could do things like add inverses to elements. And this turned out to be extremely important later when we were dealing with fields of fractions in a domain, or of a domain, for a domain. But so suppose I wanted to join now to this ring an inverse of 3. So I want to join 1/3. I mean, 1/3 is certainly not in the integers, but suppose you want to add 1/3 to the integers. Well, in fact, add it to this ring. So z adjoin root 2 and 1/3. Well, I could write that as z adjoin xy modulo x squared minus 2 and 3y minus 1. The image of y under this homomorphism then gets sent to this thing, which behaves like 1/3. So adding inverses of things could be done and is actually a very, very important sort of procedure. We saw integral domains. And integral domains are, in many ways, the most intuitive sort of rings, because I think in many ways the sort of prime ring that you always think of is the integers, and integers certainly are a form of domain, and so these are rings with no zero divisors. Which is to say that if AB equals 0, then A is 0 or B equals 0. Of course, this is false in many rings. If I consider z mod 6z, neither 2 nor 3 are 0, but 2 times 3 is 0. And that is the source of a lot of problems. I mean, so for instance, polynomials over such things behave rather differently than over a domain, or over a field. So that's useful to bear in mind. Right. And given an integral domain, as I just mentioned, there was this sort of canonical field that you could associate to that, the field of fractions. Given a domain R, we can associate to it its field of fractions, call it F. And the next topic we dealt with was maximal ideals. Maximal ideals are very important. Because we used them extensively in all of our number theoretic work that came with our study of factorization and so on. So M is maximal, of course, just by definition. If and only if the only ideals containing M are M and the entire ring. And this was equivalent to R mod M being a field. What?
Okay.
We skipped that chapter, I thought.
What?
I thought we skipped the chapter, but that's...
And I assume we did it in class. So.
Okay. Yeah. Well, I mean, it's pretty intuitive stuff. The thing about the section on maximal ideals in the book is that it starts getting into algebraic geometry. So it has this whole thing on the Hilbert-Nilstalin-sets. Now, you don't need to know anything about the Hilbert-Nilstalin-sets. If you've been reading the study guide, you would know you do not need to know anything about the Nilstalin-sets. We didn't do it in class. We didn't answer any problems on it or anything. That's algebraic geometry. And we're not doing that. But I highly recommend taking algebraic geometry at some point in your life. So the thing you mainly need to know about maximal ideals is that they're these largest ideals. They are maximal. Oh, I should mention one of the conditions that this is not, in fact, the unit ideal. It's that second isomorphism theorem that I mentioned that tells you that that's equivalent to the quotient being a field, because after all, a field is characterized by the fact that it has only two ideals, the zero ideal and the full ideal, and those are distinct ideals. And that's just, saying that the only ideals containing the thing are precisely those two distinct ideals. So there you go. Right. Oh, well, so let me just give some examples. So this is a maximal ideal in the integers. If C is any complex number, then this is a maximal ideal in polynomial ring. Those are pretty obvious because the quotient here is Z mod 3, which is one of the sort of archetypal fields we saw, and the quotient here is just C, and that's another pretty obvious field. Great. So then we started looking, yeah.
On the second example there, x minus c is
Yeah.
the maximal ideal.
So C is some fixed complex number. So I could write, E, where E is the base of the natural logarithm or something, if that's,
No,
Okay.
actually my question was going to be, I don't know if I'm having a brain fart or something, but what's the easiest way to see that that is a maximal ideal? I know it should be obvious in some way because
Yeah.
x minus c is reducible or something, or root of.
so consider the homomorphism. So I'll just return this to C. Consider the homomorphism from C join X to C, which takes a polynomial and evaluates it at C. The kernel, this is surjective, and the kernel is the principal ideal generated by X minus C. You can see that by various means, like the Euclidean algorithm on C join X. And so by the first isomorphism theorem, C join X mod X minus C is isomorphic to C. C is a field, so by this characterization, X minus C is maximal. Sorry, you have a question?
Yeah, why is that necessarily subjective?
Oh, well, I mean, because I could just take the constant polynomial, R, so R plus no higher terms, and if I evaluate R at C, then I get R. So it's surjective. Okay, great. So then we started looking at some more structured rings. We considered factorization as a sort of innately important and interesting thing. And we found that factorization is in general a very, very difficult thing to understand. But that under certain assumptions, if you start finding additional properties of the ring, like there's some sort of division algorithm, then you can make the whole process a lot easier. You can actually start disentangling how given elements decompose into products of somehow simpler elements. So again, sort of our archetypal example of almost anything is the ring of integers, and the ring of integers form a Euclidean domain conveniently. And so what's a Euclidean domain? Well, it's this thing. It's a ring. It has a Euclidean norm delta, which is this sort of, it's just some function on the non-zero elements of the ring, and it maps it to some well-ordered set. I mean, that's really all you need, a well-ordered set, although we, I think we took as our target thing, the positive integers or the non-negative integers or something like that. But I mean, that's really not the essential feature. I mean, the essential feature of the non-negative integers is just that, I have some minimal element in any subset, a non-empty subset of those, which is false in general. I mean, if I consider a non-empty subset of R, there isn't necessarily a smallest element contained in that set. I mean, I have infima, but I don't necessarily have a smallest element. But this is true, though, for the non-negative integers, say. Anyway, so we have this Euclidean norm, and a division algorithm, I mean, just some function would be stupid because I could always just define some function, but the point of the function is that it actually corresponds to something, it does something. And as part of a division algorithm, the division algorithm saying that if I have A and a non-zero B, then there are Q and R such that A equals BQ plus R, and either R equals 0 or the norm of R is less than the norm of B. And examples of such things, well, of course, Z, as I mentioned. If I have a field, oh, and so what's the Euclidean norm here? Well, just the absolute value. If I have a field, then f of x is the Euclidean domain, of course, and it has, as its Euclidean norm, the degree function. And an important consequence of this observation, that we have this division algorithm where the Euclidean norm is the degree, was that, for instance, over a field, now this is of course false in general, but over a field at least, you have a bound on the number of roots of any polynomial. This is false in general, but for fields it's true that if I have a polynomial over a field, so this implies a sort of corollary that f is a field, and if f of x is a polynomial over that field, then the number of roots of this thing f is less than or equal to the degree of f, which is a nice observation. But as I said, this is false if f is not a field. Another nice example was the Gaussian integers. So I joined square root of -1 to the integers. This thing has, as its Euclidean norm, a plus, evaluated in a plus bi, a squared plus b squared, or put another way, just the square of the absolute value function, where you view the elements here as complex numbers. And another important caveat is that this doesn't generalize to arbitrary quadratic rings. So if I adjoin a square root of d to the integers, then it's not true that the corresponding thing that we later called a norm function is in fact a Euclidean norm. I mean, so if you just give me a random thing like z adjoin square root 497 or something, that is not going to be a Euclidean domain, even though there is a sort of natural norm function on there. Well, I should say minus 497 because square root 497, that's obviously not going to work because you're going to have negative images in the to the norm. You're going to get arbitrarily negative, large negative numbers. But anyway, so it's not even true if I adjoin a square root of a negative number. Okay, in complete generality. Although there are cases where it does work. And then we saw a generalization of Euclidean domains. I mean, one of the principal things about Euclidean domains is that their ideals are principal. So we looked at that idea in greater generality. So we saw principal ideal domains, PIDs. So these are things where, not too surprisingly, all ideals are principal. And of course, as I just said, if I have something that's Euclidean, a Euclidean domain, then that's a principal ideal domain. And how did we see that? Well, obviously the zero ideal is principal because it's generated by 0. But if I have some non-zero ideal, then choose an element of the ideal with minimal Euclidean norm, and then it's not hard to show that the ideal is, and this should be non-zero, then I is in fact generated by this x. So there you go. Then there was all this stuff. Oh, sorry, was it a question? Okay. Class. There was a lecture where I tried to clear up a lot of that stuff. Now, you don't have to know lots of stuff about the relationship between prime and irreducible elements, but you should at least know the definitions and have some intuition for what's going on there. Know that, the very basics of the relationships between these things. So we had these things: prime elements and irreducible elements. And these are distinct concepts, but in certain cases they actually can be conflated, et cetera, et cetera. Another sort of generalization of PIDs we saw are UFDs. And these are unique factorization domains. So domains where you can factor elements uniquely, of course, up to associates. Into irreducible elements. And again, as I've said, this is a generalization. So if I have something that's a PID, it is a UFD. And UFDs have a lot of the things that you want most. I mean, they have sort of a notion of greatest common divisor, and they have, well, yeah, lots of good structure. And polynomial rings over UFDs, for instance, are very well behaved. If I have a polynomial ring over a UFD, then it's a UFD. Which was a useful fact in a lot of the stuff that we did. A lot of proofs are easier, actually, given the knowledge. A lot of proofs of things about like PIDs, like that the prime ideals are maximal ideals, become much simpler with the correspondence between irreducible and prime elements become much simpler in UFDs. So UFDs are very convenient rings to work in. Right. Then we moved on to Gauss's lemma. So Gauss's lemma is treated in the book as if it's something about polynomials over the integers. Of course, it won't come as a huge shock that that generalizes significantly. But you don't really need to know it for anything than over the integers. So there was this notion of primitive polynomial over the integers. And this was one where if I write down the coefficients of this polynomial, a0 through a1, an, then the greatest common divisor of those coefficients is plus or minus 1. And from that, we had this notion of content. And we proved a lemma that said something like, given any polynomial over the rational numbers, there's a unique rational number up to sign at least. Although I think it's normalized in the book to be positive or something. But that's just silly. Because that doesn't generalize. I mean, there's no notion of positive or negative in a general ring. So I mean, the good notion is just, the thing is defined, content is defined up to units. I mean, that's what you see in any higher, algebra textbook. So the content is this thing that's uniquely defined up to units, which in integers are luckily just plus or minus 1, such that I can write this polynomial as a product of the content and a primitive polynomial. This is a very, very important concept because it led to Gauss's lemma, or was relevant as an application, or combined with an application of Gauss's lemma to a lot of studies of irreducibility of polynomials. So Gauss's lemma was this thing that said that if I have f and g being primitive, then the product of f and g is primitive. And of course, this was a relatively straightforward proof. The idea was that I mean, the principle of the thing can be summarized in almost a sentence. The idea was that if a prime p divides all of the coefficients of fg, then because fp adjoin x, so the field with p elements adjoin x, is a domain, then that's saying this thing is 0, and hence that either f is 0 or g is 0, and that's synonymous with p dividing all of the coefficients of f or dividing all of the coefficients of g, which would contradict a primitivity hypothesis. And so there is no such prime p, so the GCD must be plus or minus 1, so fg must be primitive. So it's a very, very simple proof, conceptually extremely simple proof, and it was nonetheless extremely important because it gave us results like if I have an irreducible polynomial over z adjoin x, then in fact that's irreducible over the rational numbers, which is not something that's a priori obvious. I mean, that's actually a somewhat subtle statement a priori, although it comes out easily from an understanding of content and Gauss's lemma. Yeah, so those are very, very important things. Very, very important things. And then, moving along, we saw that there were various criteria that took advantage of this sort of, thing, this sort of basic irreducibility relationship to tell us, more sophisticated irreducibility relationships. So, for instance, we had the Eisenstein criterion, which said that if I have a polynomial over the integers, so call the coefficients a0 through an x to the n, this is over the integers, and a prime p such that p does not divide the highest coefficient, but p does divide the lower coefficients, but also p squared does not divide a0, then this polynomial is irreducible as a polynomial over the rationals. And I mean, it seems like it's very, very difficult to find situations where your polynomial actually satisfies these divisibility hypotheses by some sort of prime. In fact, there are interesting cases which you saw on the homework where, there were problems on the homework where there were multiple ways of showing that something was irreducible. But in many cases, one of the cleverest ways of showing that something was irreducible was to make a shift in the polynomial. So, for instance, it's pretty clear that f of x is irreducible if and only if f of x minus s is irreducible. And it is in many cases true that even though f of x does not satisfy the Eisenstein criterion at any prime, the shift of the thing does, and so that gave you the irreducibility of this polynomial and hence of this polynomial. So that's just it's a clever little trick. It's something that's nice to know. So this is the point at which we stopped doing, a lot of stuff that could be, very generalized, and we started looking at, some very, very specific stuff, namely stuff about quadratic rings and especially imaginary quadratic rings, ones that are obtained by joining some square root of a negative integer. And because it's a Euclidean domain, a great place to start is the Gaussian integers. And we started trying to understand what are the primes of z adjoint I, and how does that generalize? Well, it turned out to be fairly easy, actually, to identify the primes of z adjoint I. Now, I'm going to present the theoretical statement, the structure theory for primes in a way slightly different from the book, but one that I think is sort of conceptually more in line with why this is useful and where this goes. So, I mean, the first thing I just want to remark is that this thing, this thing is a PID. So, prime ideals are the same things, or at least non-zero prime ideals, which we're not really interested in the zero ideal. We know that z adjoint I is a domain, and that's equivalent to the zero ideal being a prime ideal. But forget about that. We know that already. It's not very important. So let me just exclude those. So the non-zero prime ideals are really the same things as prime elements. So if I have any prime ideal, it's generated by some element, and that element is a prime element, necessarily, and vice versa. And so if I start out with some prime ideal, which you should now think of as just being a prime element, as I just said, remember that a prime ideal is one that satisfies, if a product of elements is in the thing, then one of those elements is in the ideal. Then the intersection with the integers must be a prime ideal. It's not hard to show that. I mean, if I have a product of elements in here, then, well, in particular, it's in here, so one of the elements must be in there or in there, but by hypothesis, this is a product of elements of z, so the thing must be a prime ideal. We know that the prime ideals of the integers are just the things generated by integer primes, so if I intersect with the integers, this thing is just some, the principal ideal generated by some prime number. And so this is for some prime p and z. And what we saw was that we could recover all the possibilities for p for big P from little p. So specifically, if little p is 2, then there's only one possibility for the prime ideal. So there's only, the terminology used by number theorists is you talk about primes above another prime. So the primes above 2, the ones that somehow intersect the integers to give you 2, well, there's only one of those, and that's the principal ideal of z adjoint I generated by 1 plus I. Up to, this thing is, of course, ideal generators are only determined up to units, so there are a lot of other possible generators, but that's the basic idea. Yes?
The primes above 2 there, don't you, what you're saying are things that divide 2 in the ring of Gaussian integers?
Yeah, that's another way of stating it. So it turns out that and I think this is explained in the book to some extent at least, that the order relation, so an ideal being a subset, principal ideal being a subset of another principal ideal is the same thing as a divisibility relationship. And so, for fairly obvious reasons. So, yes, using that correspondence between divisibility and, the fact that, well, by definition, by construction, this thing, this is contained in this. That tells you that this must divide this. Is that clear? Great. Okay. So if I have a prime congruent to 3 mod 4, then the prime above p is, well, just p. So it's not the most interesting case. And in the case where p is congruent to 1 mod 4, then p is generated by some prime element pi of z adjoint I. such that pi bar is equal to p. So this is actually, a highly sort of exploitable consequence. And I think at some point the book, goes into, a sort of nomenclature for these three different cases. So this case, I think, is at some point called the ramified case because, this is not the same thing as this prime, but it's, the case that not the case that there's some sort of distinct conjugate. Which has its product with this thing being the prime. The square, in other words, of p squared, is the principal ideal generated by little p, well, 2 in this case. This is the inert case. Inert, p doesn't do anything, it's inert. And this is the split case, because in this case, pi bar, so then these are distinct ideals in this case, completely distinct ideals, actually equals this thing. So that prime here, or the thing that was a prime here, when I extend it to z adjoin I, splits into a product of two ideals. Yes?
Sorry, when you say p squared is equal to the prime ideal 2,
Yeah.
wouldn't it be I plus 1 times I minus 1 times its complex conjugate? Is what
if I take 1 plus I squared, I get like minus 2I or something like that. Minus 2I or 2I. And the point is that I is a unit in z adjoin I, so the principal ideal generated by 2I is the same as the principal ideal generated by 2. Great. And we saw a generalization of that, of this kind of framework, this kind of set of possibilities for how primes behave later on in much greater generality. But let me just say something else first. Something about what the generalization of z adjoin I is, because that is sort of a prerequisite for talking about how primes behave in the generalization. So suppose I start out with some sort of quadratic ring. So I've joined some sort of square root of an integer to the rational numbers. Well, we saw that there's a notion of algebraic integer. So we have the ring of all algebraic integers in there. And books calls that thing R. Another notation you might see elsewhere is O sub f. And we found that what this thing is depends on what this generator is. So I'm going to just assume that D is square free. And in some cases, this was just sort of the most obvious thing. D congruent to 2 or 3 mod 4 meant that all of the algebraic integers just looked like sums of integers plus integers times square root D. But in the other case, where D is congruent to 1 mod 4, obviously the case congruent to 0 mod 4 is impossible, because then a square, namely 4, would divide the thing, and we're assuming D is square free. So z join 1 plus root D over 2 is the ring of all algebraic integers. So, or put it another way, sums of either integers plus integers times square root D, or half integers, explicitly, truly half integers plus truly half integers times square root D. So that was good. And one of the things to explore when you're trying to understand things like primes and factorization are units. I mean, they turn up in the very definitions of things like irreducible elements. So it's good to have a pretty good idea of what the units are. And in complete generality, whether or not D is positive or negative, although I think in the book it's stated only for D negative, in complete generality, the units in the ring are the elements whose norm are plus or minus 1. Now, of course, if R is imaginary quadratic, norms must be positive. So I could have equally well said if D were negative, that this is the set of things with norm alpha equal to plus 1. But if I want to include the real quadratic ones, the ones that I get by joining some positive integer, square root of a positive integer, then I need to include negative 1 there. So, and the proof of that was pretty obvious. And of course, by the norm of alpha, or better put, the norm of a plus b root d, so these are either integers or half integers according to the case of d. Is a question?
Sorry, dumb question. Why would you want negative norms?
Well, I mean, in the case where I have d being positive, the norms could be negative, right? I mean, I could have something with norm negative 1, but by the same proof, that's obviously still a unit, right?
Sure.
So it better be in there.
Yeah.
I mean, so for instance, let me think, see if I can think of an appropriate unit. I mean, if I look at 1 plus square root 2 or something, the norm of this is negative 1, right? Because it's 1 minus 2. That's negative 1. But it's a unit, because I could multiply this by negative 1 minus root 2, and that's equal to 1. So this is clearly a unit, but its norm is negative. Is that clear? Great. So this is a plus b root d times a minus b root d, or put another way, a squared minus b squared d. So of course, if d is negative, then this number is always positive. But if d is positive, then this could be very, very negative, or it could be minus 1, it could be anything. Well, not anything. Not anything, but well, anyway. There you go. OK, and then in the explicit case where d is negative, you could say more. I mean, in the case where d is positive, there are tons of units. They're just like flowing out of your ears. In the case where d is negative, it really becomes a much simpler sort of situation. So you can give a complete sort of list of all the possibilities. If d is minus 1, then these are the units. In other words, in the Gaussian integers, and we already knew that. In the case of d being minus 3, letting zeta 6 denote a sixth root of unity, all of the powers of a sixth root of unity form the units in that case. And then if d is anything else negative, then it's just plus or minus 1. It's pretty easy to prove that. Yeah. Oh, yeah. So the next thing, I just want to make one last comment, and that is, in studying the prime ideals of a more general R, the crucial thing to sort of bear in mind is that you have this sort of relationship, say R mod P is the same thing as Z adjoin X modulo, well, either X squared minus D or X squared minus X plus 1 minus D over 2, depending on what case you're in, whether this is the D congruent to 2 or 3 case, or congruent to, or in the D congruent to 1 case. And this thing is then just FP join X modulo, well, again, either X squared minus D or this other polynomial. And so that tells you a lot. So for instance, this allows you to say things like, well, I can say that something is maximal, a prime, an integer prime is maximal in this quadratic ring by looking all the way over here and seeing that the polynomial over here is irreducible, and hence generates some maximal ideal, and hence this thing is a field. And so then lifting back here, you knew that that thing was maximal. So I'll answer more questions after I disconnect myself, but I need to let him go. So great.